Hello there, everyone. Assalamu alaikum. Now, I think we can officially start A2 physics. But before we start, I want to show you a video. So, our first chapter is circular motion, right? But before we start, I actually made a video for you guys while I was ill. Hey, salam, guys. So, let's start off with circular motion. But before we start off in a boring way, the old-fashioned way, let's actually look what circular motion is. Can you guys look up for a second? What do you see? Exactly, a simple fan. That's the best example of circular motion at your place. This to this. Finally, this is circular motion. Yeah, guys, in our real lives, circular motion has some very amazing examples. And before I end this video, let's check this out. Pretty fun, right? Well, that's circular motion, so I hope you guys enjoyed this video. Now let's start off with our first lecture. Alright guys, so that's it for the video. Circular motion is all around us. And in case you guys are wondering, did you know that our own planet, the whole solar system, the Earth and the Sun, that's circular motion. We are literally standing on the phenomena of circular motion. Now, let's start the class. Now, before we start off, I have a question. Do you guys know Jeetu Pakistan? Do you guys watch Jeetu Pakistan? I know it's a bit weird, it's a bit sudden, but do you guys know Jeetu Pakistan? Come on, guys. Yeah, right? So for those who don't know, this is like a game show where you win stuff. Now, let's say we've been to Jeetu Pakistan, right? And we want a car, right? We got a car. So let's make a car. And it might not turn out so well. Okay, so that's our car. And let's make a road. Now, if you have a car, you obviously want to drive it, right? Now, let's say our car, it travels, I don't know, a distance of around 1,000 meters. Hey, whoever has his mic on, can you please turn it off? And whenever you have a question, just raise your hand and you can turn your mic on. So if any of you has his mic on, please turn it off so we can have better attention. Now, the car, it travels a distance of 1,000 meters. Now, let's say it travels this distance in, I don't know, 5 seconds. All right, guys, now it's a question for you guys. Does this car have velocity? Does it have a speed? And if it has a speed, can you guys please help me out finding it? Come on, guys. Let's find the speed. What is the velocity of this car, which traveled 1,000 meters in 5 seconds? Yes, so Sabina, you're right. The car has a velocity. Come on, guys. So speed, that distance is speed into time, right? So what is the speed? Yeah, exactly. Amazing. So we're going to write distance as displacement, and it is usually written as an s. So a small s divided by time, that's our speed. So it's going to be 200 meters per second. Now, I am assuming that this car has a constant speed from point A to point B. But can you guys tell me, do cars accelerate? I mean, do cars accelerate? Yeah, yeah. So obviously, it's going to have some kind of acceleration, right? Now, we are going to bring our car into a different situation. Now, let me select all of this, and I'm going to try to change the size. Okay, just a second. All right, so, oh my God, the car is literally gone. Okay, so let's move this here. Now, in Urdu, it's called Gol Chakkar, but in English, it's called a roundabout. Now, let's imagine that our car, it's in a roundabout, right? So let's make our car, and it is traveling around this roundabout. And now I want you guys to be attentive. Now, what I just did, this above is called linear motion. So this situation above is the linear motion. But what I made here, right here, this is circular motion. And this is the best example of the contrast between these two motions. Now, unless you have a Hulk who's literally spinning your car, now that's a different scenario, but that would also be an example of circular motion. Now, guys, does this car have a velocity when it's traveling in this motion? Does this car have a velocity? And if it has a velocity, can you guys tell me its direction? Where is the velocity? Is it towards the left, towards the center? I don't know. Where's the velocity? There's a term that's used for it. Exactly. So amazing, Aima. The velocity is tangential. So I'm going to use a reddish color to represent this. Now, this thing right here is our velocity. Yeah, Abdullah, I'm going to talk about that too. So this is our velocity, and it is tangential. Now, there's one very interesting thing. Anyway, so in our situation above, our car was accelerating, right? Now, can you guys please tell me, in this circular motion, is my car accelerating now? Now, there's one thing you have to keep, in your mind. Our velocity, the magnitude of our velocity, the speed is constant. I'm assuming that the speed is constant. So keeping this at the back of our brains, is the car accelerating now? Can you guys please answer this question? Yo guys, is the car accelerating? Yes, Aisha.
No.
Why is the car accelerating? What is your reasoning? One of you answer.
No.
Okay, so why is the car accelerating? I need a genuine reason. Yeah, the direction is changing. Now, pay attention, everyone. Now, we know that acceleration, acceleration, it's a vector. Acceleration is a vector. And you know that vectors, they have a magnitude, right? They have a magnitude and they have a direction. So if any of these is changing, we say that this is also changing. So because the direction is changing, you can see that the velocity at point A, it's pointing upwards, but at point B, it's not pointing upwards anymore. It's pointing towards the right. So because the direction of VA and VB is different, the car is accelerating. So let's write it down over here. So the car is accelerating because the direction of velocity is changing. All right. Now, there's one last thing. In this circular motion, do we have a resultant force? What do you guys think? In this scenario, do we have a resultant force? Can anyone answer this question? Exactly, Varun. Now, what is the direction? Yeah, Aima, amazing. So, yeah, you're right, but we're not going to get into that yet. This is what we call in A-levels the centripetal force, but we're going to talk about that later. For now, let's just keep in mind. Now, this is our force. Now, this is called the centripetal force, but right now, we're not going to get into that because it's not the topic for today. And in case you're wondering, this acceleration, it is also pointing towards the center. Now, there's a very fun thing that I want you guys to look at. Now, what is the formula for force? Come on, guys. What is the formula for force? What is the formula for force? Yeah, ma. So F is ma. And we know that in this equation, mass is a scalar, right? So mass is not contributing towards our direction. Now, if acceleration is multiplying with the mass, so this is the only vector we have in our equation. So that means whatever direction acceleration is going to have, the same direction the force is going to have. So this is one way of remembering why acceleration and force have the same direction. Now, I want you guys to take a screenshot or something, and once you're done, we're going to move on to the actual chapter. This was more of a recap. In case you're wondering, all of it was done in O levels, but I still wanted to make sure you guys knew. Okay, done. That's great. I'm still saving the screen, so if anyone isn't able to, take the screenshots, I can still share with you later. Now, let's erase everything. Now, in our previous scenario, in our linear motion, right? Let's make two labels, right? This is linear motion. So in linear motion, our car was displacing. So there was this thing, it's called linear displacement, right? Linear displacement. But in circular motion, I want you guys to look at this. Now, this is my circle, and I'm going to be using an arrow to represent the motion of our car. So let's say our car is moving from this point to this point. Now, can you guys notice for a second? In our previous scenario, let's say our car is moving from here to here. It's displacing linearly. But now in circular motion, it's moving like this. So let me make a line first, and I'm going to ask you what changed. Now, just give me a second. I'm going to make a line over here, and I'm going to make another arrow. Now, one of these situations is going to be point number A, and the other is going to be point number B. So this is point A, and this is point B. Now, can anyone tell me what is the difference between these 2 points? What changed from moving from point A? Exactly, Varun. So angle is the thing that's changing. So back in the previous scenario, I was having displacement, right? Meters, displacement in meters, distance is changing. But in circular motion, angle is changing. So in this scenario, what actually changed is the angle. Now, if I want to ask you, what is my angular displacement in moving from point A to point B? Can anyone answer that question? What is my angular displacement in moving from point A to point B? Does anyone know the answer? Exactly. So how do I find, basically what I asked you was, if I use a red marker and I make this arrow, this is my angular displacement. Exactly. Theta 2 minus theta 1. All right, let me make it using a black marker. Okay, so theta 2 minus theta 1, this is my angular displacement. But we still haven't officially studied angular displacement, so let's look into that. Now, this is the best example I could give you on what is angular displacement. Yeah, we're going to talk about that later. Now, let's make an official heading. Angular displacement. This is the first definition of our chapter. So, angular displacement. All right, so the definition for this is an official one. So we say angle subtended by an arc at the center of the circle. Now the symbol of our angular displacement, that's a simple theta. That's our symbol. Now, can anyone please tell me, what is the unit? What unit do we use to measure angles? Exactly. Now, in this scenario, you might be wondering, okay, so my whole life, I've been studying that angles are measured in degrees, 50-degree angle, 360-degree angle, 20-degree angle. So why radians? Because that's our standard unit. We use radians. This is the standard we use in physics. We use radians. We don't use, the normal angles. Now, I hope everyone is familiar with this word because last time in our demo class when I was teaching, a lot of people were asking, I mean, what is subtended? So, आसान लफ्जों में, in Urdu, we say कि, from point A till B, एक angle बन रहा है. So like, this is एक angle बन रहा है यहाँ से, इस point से लेकर यहाँ पे. So this is basically that thing, angle subtended by an arc. Now, if anyone doesn't, yeah, formed, that's a better word. Now, I hope you guys know that what is an arc, because when I was studying this chapter back in the day, I kind of got confused. I thought that this thing was an arc, but an arc, let me use an orange marker. So this is my arc, right? This is my arc. This is the arc. So just in case anyone has a confusion. Okay. Yeah, exactly. So this is the arc. Now, angle subtended by an arc. So angle is being subtended by this arc at the center of this circle. So you'll just have to remember it. Now, I want to make sure that you guys know this. Can anyone tell me what is pi radians? What is pi radians in the normal degrees? I want to make sure that all of you know how to convert these. Exactly, 180. So pi radians is 180. Okay, so what is 2 pi radians? What is 2 pi radians? Come on, guys. I know you can do this. Exactly, 360.
360.
Exactly. Now, we're going to do one last thing. What is pi by 6? Now, it's a bit tricky. If you mess up, don't worry. Pi by 6. It took a while. All right, so yeah, it's 30. You just divide 180 by 6, and the answer is 30. All right, so this was just to make sure you guys know. Okay, you guys can take the screenshot, and yeah, we're going to move on to the next thing. Okay. So tell me when you guys are done. Okay, so Abdullah, a circle has 2 pi radians. You can exactly divide a circle into 6.62. I don't know about that, man. All right, so great. All right, so I'm gonna save the screen as well. Okay, so I'm clearing this up. All right, so now in our previous scenario, the linear motion. Now let me make the car again. Okay, let's just use a block. All right, so a block. So I'm gonna use a black line. Now, the block is traveling, let's say, I don't know, 200 meters in 5 seconds. So when we say that this block has a speed, we are basically saying that 200 divided by 5. Can anyone please find this? What is 200 divided by 5? Come on, guys. What is the speed? Yo, guys. Okay, yeah, 40. So my speed is 40 meters per second. So this is, in other words, okay, what is the definition of displacement? Can anyone please remind me? O levels, displacement. In fact, I think you guys even studied that in AS. So what is the definition of, the velocity? What is the definition of velocity? How do I define velocity? Can anyone tell me? The definition of velocity. Yeah, displacement per unit time. So we can say rate of change of displacement. And we can also say displacement per unit time. Now, I'm going to tell you guys why I told you this. Now, as the car is traveling a distance in a particular amount of time, it has a velocity. Now, let's clear this up. Now, we have our angular motion or circular motion. Now, in this scenario, let's say I have this arrow and it's moving from here to here. So it is traveling in terms of angle. So it is angularly displacing. Now, if I want to find its speed, that's going to be the angular speed. And this angular speed or angular velocity, call it whatever you want, angular speed is going to be rate. Okay, I'm going to tell you guys. So what is going to be the definition of my angular speed? You know that I am basically traveling in terms of angle. So I am angularly displacing myself. Yeah, exactly. Oh, rate of change. Bro, yeah, exactly. So well done, good job. So the definition is going to be rate of change of angular displacement. And this is a very interesting contrast. Now, if we were to basically see, this is how our let's you guys know yo-yos, right? So let's say this is a yo-yo and it moved from position, I don't know, position A. So our yo-yo, it moved from position A to position B. So it traveled this angular displacement. Let's say this was theta 1 and okay, theta 2, and this was theta 1. So this is theta 2 minus theta 1. So this is going to be our angular speed. Let me actually make it a bit neat. Okay, so our yo-yo moved from that position to that position, and this is our angular speed. Now, for now, I want you guys to keep at the back of your brains. Okay, so Huzaifa, good question. It's angular speed and velocity, but we actually write it as angular velocity. Why? Because you know that velocity is a vector and displacement is also a vector. So if I said rate of change of angular distance or something like that, then it would have been angular speed. But when we discuss this term, we can call it angular speed and angular velocity. But for you guys, let's just go with angular velocity. Now the symbol of this new term that I just introduced is omega. This is the symbol of angular velocity, and this is a completely new symbol for those who are studying A2 physics for the first time. Now, I discussed the logic we use to find the units. Can anyone please tell me what is going to be the unit of my angular velocity? Can anyone tell me? What is going to be the unit exactly? Radians per second. So we can write it like this, radians per second. So this is the unit of our angular velocity. Now, there's something very important I want you guys to know. When I was studying this chapter for the second time, I was shocked when I found out. Now, usually in exam, in book, examiners and teachers are always going to show omega or angular velocity as this. And for now, keep that at the back of your brains, that this is our angular speed. You know, this is a curved arrow. But in reality, the direction of angular velocity is completely different. I'm going to talk about that later because I want you guys to absorb these concepts first. Now, let's discuss the formula for angular velocity. Okay, so Abdullah, you have a question. You just raised your hand, so you can turn on your mic and you can ask me a question, or you can just use the chat. Okay, so okay, no problem, no happens. All right, so now the formula for our linear velocity was displacement divided by time, right? But what is the formula for my angular velocity? You know that this is the rate of change of angular displacement, or angular displacement per unit time. Now, if you know that definition, you should be able to tell me the formula. Can anyone please tell me what is going to be exactly? Theta divided by time. This is the formula of angular velocity. So this is the formula for angular velocity. So this is the linear velocity, and this is the angular velocity. All right, now I have a little fun. You know, before we do that, I want to tell you something. Let's say we are talking about one revolution, one circle. So we have a yo-yo, right? You know, in our childhood, we used to play a lot with these things. So it's a yo-yo, and I'm spinning it like this. And let's say I am completing one whole circle, right? I'm making one whole circle. Now, the circle looks really bad, but that doesn't matter. So I'm making one whole circle. So if I want to find omega for my one circle, one revolution, let me use an arrow to show you this. So this is my yo-yo, and it is making one circle. So what is going to be my angular displacement, guys? So what is going to be my theta? What is going to be my angular displacement for one circle? Can anyone tell me? For one revolution, what is going to be my exactly, Abdullah? Now, it's going to be 2 pi. But there's one more question I have for you guys. Yeah, guys, it's 360 degrees, but don't forget that in circular motion, for all calculations, you use radians, unless specified. It's always radians. So 2 pi. Keep that in your mind. Now, I know it's going to be a bit weird, but can anyone tell me what is going to be the time for one revolution? I know I have provided you with none information, with not even a single amount of information, yet I'm still asking you time because you should be able to know it. Okay, so Ima, good job. Now, let me explain what she just said. It's the time period, the capital T. Now, I want you guys to recall something. In O levels and even in AS, now in AS, we studied this concept of, this a pendulum, right? So when I say that this pendulum completes one oscillation, this time isn't called time, right? It's called the time period. So for one oscillation, the time is time period. But since we are talking about circular motion, the time for one revolution is going to be my time period. So one revolution. So the time for one revolution is going to be the time period. So there's this general formula that we get over here, and it is, oh, not theta, lol. Okay, so it's going to be omega is equal to 2 pi over t. Now, this is a general formula. So whenever you have a motion where there's one revolution or the time period is involved, you guys can always use this formula. But is this clear, guys? Is everyone clear about this? Does anyone have any kind of confusion about this concept? Oh, okay, that's great. So I hope this is clear. Now, there's one very amazing thing we can do right here. Now, can anyone tell me this formula right here, it can be rewritten as something else. One thing can be tweaked over here, and this formula can be written as something else. Does anyone know? Yeah, I'm amazing. Now, we know that the time period is basically, 1 over frequency, right? We studied this in O level, right? So if I substitute 1 over f into this, I am going to get another new formula, and it's going to be 2 pi f. So let's say you have a question, right? And they haven't given you the time period, and you're a bit, you want to do the question in a shorter way instead of calculating the time period. No problem, Shamir. So you can just use this directly. Now, take a screenshot, and I am going to erase everything. So once you're done, tell me. I mean, unless you're making notes. So if you're done with the notes, tell me. Okay, are you guys done? Great. Now, let's erase this. Now, there's one thing that we have to officially write. All of us know what is time period, but we got to write the definition. So the time period, or the capital T. Okay, so the definition of time period, the time period's definition is going to be simply, no fancy English, just time taken for one revolution. So if they ask you in the exam, you can literally just write it. You don't need to specify some hard formulas. Yeah, so you know the formula. So time taken to complete one revolution. I think that works as well. Now, there's something we want to do. Let's recall an O-level maths concept. I hope all of you studied well in your O-levels, because if you didn't, it's gonna, okay, so I literally wrote O-math, LOL. It's O-level math. Okay, so it's not O-math. Okay, so O-level math concept. Now, in O-levels, I don't know what was the name of that chapter, but all of you studied this concept of arc length and angle. For some, it might be a deja vu or something, but for those who didn't study, it might be a completely new concept. Now, this is my radius, let me use a different color for this. So this is going to be my radius, right? That's my radius. And this is my theta. Now, can anyone please tell me what is the symbol of this thing? What is this thing called? Okay, first, what is this thing called and what is the symbol that I use to represent it? Can anyone please remind me? Exactly. It's not the arc, guys. It's the arc length. I know this is the arc. Yeah, this is the arc, but the specific word for it is arc length. Now, can anyone please remind me the formula that relates all these three terms, S, R, and theta? There's a formula that relates all of them. Exactly, Abdullah. That's amazing. So the formula is S is equal to R theta. This is a formula from O-level math, but now we are going to be using it in A-level physics. Yeah, right. Arc line is radius into angular displacement. Now, let's move this formula. Let's select it and let's move it right here because we're going to be doing some derivation. This is going to be, I think, the first formula that we're going to derive today. Okay. Now, there's something very fun that we can do over here. What if I say, okay, guys, so what if I say that I want to divide both of these sides with time, with a t? What do I get over here? What is S divided by t? Come on, guys. Okay, I'm opening the chat. Yeah, it's the linear displacement. So in case you're wondering how in the world did we get linear displacement in circular motion, do not forget tangential velocity. I literally taught you that at the beginning of the lecture. Now, this is going to be the linear velocity. Now, can you guys tell me what will I get over here? What is going to be here? Come on, guys, I literally just taught you. Exactly, omega. It's going to be omega. Now, if you actually open your eyes and look at it, we literally just derived our first formula. This is the first formula we just derived. But never forget that this thing, this thing over here, this is our linear velocity. This is the linear velocity, and this is our angular velocity. So note this down, and we're going to do a fun question. So take a screenshot or something, and we're going to do a fun question. It's going to be a bit confusing, I guess, but it's a very fun question. Okay, so are you guys done? Have you taken a screenshot or something? Or have you noted it down in your notebooks? Okay, I'm going to wait for you. Okay, let's wait for Varun because he is still noting. So Varun, whenever you're done, I'm going to erase everything with a single click. Okay, amazing. Now, if you actually look towards your wall, you're going to see the clock, right? Now this, no problem. Now this is the moment when you're going to kind of feel sorry for not paying so much attention to it because it's officially our first question. All right, so the English might be a bit hard. No, I don't think so. It's going to be easy. Okay, so the minute hand, okay, so the minute hand of a large clock is 3 meters long. All right, so what is its mean angular speed? So I'm going to give you guys a little while and let's see what you can do. I hope everyone knows what's a minute hand. If anyone has problem understanding this question, you can literally just ask me. But it's a very fun question. I loved it when I looked at it first time. All right, let's see who finishes it first. I have the answer right in front of me, so I can instantly identify who does it correctly and who does it incorrectly. Okay, so it seems everyone is solving the question. Okay, so Lisa's answer is 0.105. So I'm obviously not going to tell you if the answer is correct because I want to see how all of the other students do because we literally have like 18 participants in this class and we just have one answer. All right, everyone, we just have two answers so far. So I want an answer from every single student in this class. Otherwise, I won't tell you the right answer. Come on, guys. Okay, guys, so I'm giving you guys last 2 minutes. So it's 4:43 p.m. right now. When it's 4:45, I'm gonna end the time. All right, let me tell one thing. So far, we don't have a single right answer. LOL. No problem, guys. It's a bit tricky. Okay, guys, 1 minute left. In fact, 1.5 minutes left. Yeah, Baron, it's right. It's literally just theta over time, but it depends what values you put there. Come on, guys, 1 minute left, and we literally have. All right, let me count the answers. So we have an answer. You know, it's 1, 2, 3, 4. Literally 4 answers. Come on, guys. There's like 18 participants in this chat. All right, even if you have a wrong answer, come on, guys. I want your answer. Always be confident with any question you have or any answer you have. Because if you don't try, how will you improve? Okay, the answers are kind of getting closer, guys. All right, so 1 minute is almost up. Come on, guys, all of you. Okay, time is up. Those who weren't able to solve, no problem. Okay, Abdullah, let's see if you were right. Now, let me make this situation. Let me draw this, Okay, so this is our clock, right? Thanks for the circle, because if I didn't have it, the clock would have been terrible. Now, in our clock, it's very important for you guys to know, come on, you're A-level students. We have two hands. There's the smaller hand and there's the bigger hand. So let's say it's 12 and it's 1. So the time on the clock is going to be 12:05. So this 05, this is our minute hand. And let's use a red color to represent it. Now, pay attention, everyone, because this is important. Now, our minute hand, it actually travels from point A, like this, and it comes back over here. Now, you know that in a single day, we have around 24 hours, but the clock has 12 hours. So this small stick right here, it travels around 12 hours. So it takes 12 hours for it to complete one circle. Meanwhile, our minute hand, it takes 60 minutes. Come on, guys. Everyone knows that 1 hour has 60 minutes, right? So can I say that the time period for my minute hand, making these turns is actually 60 minutes, right? But that's still not it. Now, we know that omega is, theta divided by time. But pay attention over here. In this question, we were given the radius. So some of you, they might have been confused that, okay, so we have radius, so okay, we're going to put it somewhere. But all of you know that angular speed is literally just theta divided by time. Now, my theta is going to be 360 degrees, or in other words, 2 pi. But my time period, it's not going to be 60 minutes. It's going to be 60 into 60, meaning 3,600 seconds. And the answer I have on my, the answer section is 1.7 into 10 raised to the power minus 3 radians per second. Okay, does everyone understand this question? It can be a bit tricky. If anyone has, no problem. I kind of got it wrong the first time too, don't worry. Okay, so does everyone understand this question? Come on, guys. Literally, there's a lot of students here and just 1 or 2 are telling me. Okay, come on, everyone. I want an answer from you. Okay, so Eliza, what is your confusion? What part do you not understand here? Okay, Eliza. Now, okay, so I assume that's the only confusion. Now, In A-level physics, be it AS or be it A2, we know that the base unit of time is seconds. So no matter what kind of calculation you're doing, time is always in seconds. Mind it, keep it, note it down. If you have a chart paper in your room, just write it down on with big letters. So in physics, time is always in seconds, unless specified. So unless they specify, always in any kind of calculation, use the time in seconds. Okay, so Sabina, the 3 meters. Now, in questions, not even in this question, even in CIEs, they give us a lot of information. But I always think, do we need that information, or are they just confusing us? So I assume that this piece of information was given because there's another part to this question, or they wanted to confuse you guys. All right? Now, there's a very interesting thing that I want you guys to pay attention here. Okay, now pay attention, everyone. You just found, you just found out that it doesn't really matter what is my length, right? So if my minute hand, even if it was like, I don't know, 100 meters or 1 kilometer, what really matters is the time period, right? Because my angular speed is 2 pi over t, right? So it kind of doesn't really matter what is my length, even if this is like 0.2 centimeters, but the time taken is the same. That is what matters. So it's a very interesting observation over here. Okay, now, everyone clear? Take a screenshot and tell me when you guys are done. We are going to move on to the next little concept. Okay, so are you guys done? Has everyone noted it down? Yeah, it doesn't matter, Aima. It doesn't matter at all. But only if you're calculating the angular speed. Only the angular speed. Okay, now I'm erasing this. Now let's actually go to this concept. Now this is the thing that I did that day in the demo class as well. Okay, so in the exam, there's going to be a lot of questions like these. So define radian, define Kelvin, define Tesla, define. Now, whenever you see these questions where they ask you to define stuff, you have to keep one thing at the back of your brains. If they said define radian, they're talking about 1 radian, right? 1 radian. Keep that at the back of your brains. So if there's one concept that you're gonna learn later on in A-level physics is Tesla. So if they say define Tesla, they're saying tell us the definition of 1 Tesla. So this 1 radian is very important. All right. Now we know that radian, it's the unit of angular displacement, right? And we also know that angular displacement has a formula, which is S is equal to theta r. Okay, 1 radian is the angle required for each part of it. Okay, so this might be a good description of it, but there's a proper definition, and we're gonna get into that later. Now, we know that theta is S divided by R. Okay, everyone, it's a question for you. How can I get 1 radian over here? What do I do over here? What values do I put here to get 1 here? Come on, guys, any kind of thing that comes up in your mind. Yeah, I want to get 1 over here. I want to get 1 radian over here. So what values do I put? Both of them. Yeah, Abdullah, that's right. So either both S and R are going to be 1, right? No, it should be. We want 1. We want to get 1 out of this because that's what we need. Now, to get theta equal to 1, right? If we want to do this, 1 is equal to theta, there's only one possibility. Either both of them are going to be 1. So 1 divided by 1 is 1, but we don't really need this in A-level physics. What we need is this. We want to make S and R equal. So this is the thing that's important. So S is equal to R. So if both of them are equal, theta is going to be 1. So if S and R is equal, my theta is going to be 1. So if I want to describe it in words, right, it's going to be like this. So 1 radian is the angle, but this is not the definition, mind it. This is not the definition. So 1 radian is the angle if S is equal to R. Keep this at the back of your brains. Now, we're going to write the proper definition. And unfortunately, you're going to have to remember it. But don't worry, there's a lot of opportunities for you to master this definition. Now, the proper definition is, this is, by the way, the CAIE definition, right? Okay, so angle subtended. You should be getting deja vu right now because we just did this. But there's one more thing to it. Okay, so angle subtended by an arc at the center of the circle equal in length to the radius. Now let's observe this. Now, angle subtended by an arc, right? Isn't this the theta? Isn't this talking about the theta? Now, at the center of the circle equal in length to the radius. So what it actually says is, it says this, it says that if my arc length, by an arc of length equal in length to the radius. So it's basically suggesting the same thing we just did. It's saying that if S and R are equal, that's radian, that's 1 radian. So does anyone have a problem with this definition? You can think of any ways to remember this, but this is the definition. Does anyone have any kind of confusion over here? Okay, it's clear. All right, I want an answer from I want an answer from everyone. Come on, guys. There's a lot of students here, but I just see 3 to 4 answers. Come on, guys, everyone. Is it clear? Do you have any kind of confusion so far? Because, okay, Rayan. So, Rayan, what did you exactly not understand? Can you please elaborate what did you not understand? Rayan. Okay, so I'm going to explain one last time for Rayan. So, Rayan, I'm going to simplify this. When they say define radian, what they're saying is tell us what is the definition of 1 radian, right? They're asking us the definition of 1 radian. And I just said that if I want to get 1 radian as my angle, S and R have to be equal, right? Because we know that 5 over 5 is 1, right? Even if this is, I don't know, a million, in fact, this is just 10,000, but even if this was a million divided by million, this would have been 1. So it doesn't matter what number I have. As long as S and R are equal, my angle is going to be 1 radian, right? Now, what I've done over here is I've just literally, in a more beautiful manner, said the same thing this thing says. So I am saying that angle subtended by an arc at the center of the circle. Now, till this point, this is the definition of angular displacement. This is the definition of my theta, right? Now, angle subtended by an arc at the center of the circle of this part equal in length to the radius. Now, till this point, it is telling us about the angle, but by an arc. See, angle subtended by an arc equal in length to the radius. So this thing says that my arc, my S is equal to R. So R and S are equal, and this theta is the angle which is being subtended at the center of the circle. Okay, so I hope this wasn't too complex. Do you get it now? Rayan, do you understand now? Rayan, please answer. Do you understand now? Okay, that's amazing. Now, let's clear this, and we're going to do the last concept for today. And this is, guys, the legendary centripetal acceleration. All right, so can you guys remind me that, let's say I have a car, I have a car over here, and the car is traveling in this circle, right? Okay, just a second. Let me use a marker. Okay, so, okay, LOL. Let me bring back the circle. All right, so the car is traveling in this circle. Now, can anyone tell me what is going to be the direction of my velocity? The car is traveling in this circle, but what is going to be my velocity? Oh, what is going to be the direction of my acceleration? Can anyone please tell me? Yeah, the velocity is going to be tangential. And what is going to be the direction of my acceleration? A, acceleration A. I just told you guys at the start of the class. Yeah, exactly, exactly. The acceleration is going to be towards the center. Now, pay attention, everyone. Now, there's a name for this acceleration. This isn't just any acceleration. This is the legendary AC. We write it as AC. So this A represents acceleration and C represents, centripetal. So this thing is called the centripetal acceleration. Now, what we're going to do is we are going to derive this. Now, if there's anyone in this class who watched the video I sent, now the video was made by Sir Narshir, and there's a lot of ways to derive acceleration. There's so many ways. You can open one book, they're going to tell you one thing. You will open another book, they'll tell you another thing. But from what I've seen is that the easiest way to derive this is the one that I'm going to tell you. So this might be simple, and once you get the simple one, you might be able to understand the complex one as well. So let's make a few changes to this diagram, and let's make this. Okay, so now we're not talking about a car anymore. We are talking about the, okay, so we have this line over here. This is our point A, and this is our point B. Okay, so let's use a black marker. Yeah, Varun, but we want to derive this. So we are going to derive the same thing you just said. Okay, so this is point A. Let me use a marker. Okay, so this is point A, and this is point E. Now pay attention. If you miss my word, you're going to miss the concept. So at point A, I have a velocity, and velocity is tangential, just as you guys said. So velocity is tangential. So I can easily say that this is my VA, right? VA, velocity at A. Now this is my VB, velocity at B. And I will say that this thing right here, this is the change in arc length because it's moving from point A to point B. So this is the arc length, but we're going to write it as change in arc length. And this is my angular displacement. So I'm going to say that this is change in theta, change in my angular displacement, right? Now, keep this at the back of your brains, and now we're going to make something amazing. Oh, by the way, and this is also our radius. So these are our radiuses. Now, let's draw the vectors. Now, in O levels, you have done this concept. You might have done this in AS. I don't remember anymore because I've done the AS pretty long ago. So this is my VA, and this is my VB. Now, this is the scenario if I take this vector and this vector and I place them like this. This is going to be my situation. Now, let's label this as VA, and let's label this as VB. And this thing right here, isn't this also going to be our angular displacement? Resultant is not actually going to go inward. Now, there's one thing. I'm going to make an arrow to show the resultant, and this is my resultant. Now, in case you're wondering, why did I make the arrow upwards, right? I mean, I could have easily said that this arrow can go from this point to there. But tell me, which one of these velocities came first in time? Yes, it's VA because VA happened first, right? So if VA happens first, this means that if there's a resultant, it's obviously going to move from here to there because it happened first in time. So just if you have this confusion. Now, this thing right here is also going to, this angle that it's making, it's literally going to be the same as this. So this is also going to be our change in theta. And I'm going to call this as change in velocity. Now, let's move our, okay, just a second. Let me move these a bit towards there. Okay. Let's move this here, and let's move this here. Now, what we're going to do is we're going to draw this thing now, this arc, this sector thingy, exactly like this. So this is gonna be my radius. Okay, just a second. Let me use a black color. Okay. Now, if we were to draw it like this, you would notice that these radiuses have the same angle as both of the velocities. Now, there's something I want you guys to understand. Now, if I were to make the arc, it would obviously look like this, right? This is my arc. So if I were to make this thing over here in this fashion, my arc would have been a curve. But there's something very interesting I want you guys to understand. Have you guys seen pendulums? I've mentioned this before as well, but now there's one more thing that I want you guys to know. Now let's imagine, you know, that if this pendulum is moving from this point, point A, to point B, just a second, let me move this bar first. Okay, so if my pendulum is moving from point A to point B, it's moving like this, right? In a curved way, right? Now pay attention over here. But what if my angle was small? What if my theta was small? Let's imagine that. So if my theta was small, let's try to imagine that. If my angle was small, you guys would notice that if it's moving a little bit, it would not be a curve anymore. If my angle is small, it would move in a straight line. And that's what I want you guys to understand. And that's the very reason I am giving the example of a pendulum and not our scenario. So if our theta, if our angle is small, if our theta is small, theta, small. Now this thing would be a straight line. This would be moving in a straight line. Now, if pendulum moved from this to this, what if I would decrease my angle in circular motion? Let me actually show it in circular motion. Now, let's imagine that I have this circle, okay? I have this circle, and I am making my angle, but my angle is small. If my angle were to be, now, obviously, I cannot possibly show you how small it should actually be, but you guys know that in reality, this is how small the angle is, all right? This is how small the angle is, but just for the sake of explaining, I'm gonna move this thing over here. So if my angle is small, if my theta is small, if my theta over here, if this is small, this would not be a curve anymore. This would be a straight line, a straight line. Now, theta is small. This is a side note. If my theta was small, the change in S, the change in arc length, it would not be a curve anymore. It would not be an arc anymore. It would be a straight line, and I would call it change in arc length. Now, do you guys understand this part? I want a response from everyone. Do you guys understand this? Because it's very important to confirm that you guys understood this. Okay, so if anyone has a confusion here, you can ask me, because this might be confusing. I myself got a bit confused that how can an arc turn into a straight line? Okay, that's amazing. So just a side note, not an arc anymore, but a straight line. Now, you guys studied in O-level maths the concept of similar triangles, right? So first, let me select this and make this small. Okay, I'm decreasing the size and I'm going to move it over here. All right, so now, if we actually observe these two triangles, both of them are similar. Why? Because the angles are the same, right? Because the angles are the same, the triangles are the small. So I can say that, let's say, let's actually use the book style teaching. So the book, what the book does, they always tell you different alphabets. So they use the alphabet. So this is the point A, this is point B, this is point C. So this would be point D, E, okay, E and F. Now, can anyone tell me which of these sides are similar? Come on, all the similar sides, right in pairs. Which sides are similar? You can say, like, let's say, yeah. So which sides are similar? Use the alphabets to tell me. So for example, CB and FE, these sides are similar. So what are the other two? Yeah, Aisha, it's AB and DE. And there's one more, guys. There's one more. You're missing on one side. There's one side left. Yeah, so Abdullah chose the easier way of spelling. So yeah, exactly. So the similar sides are technically the same sides because they're the same triangles. They're the similar triangles. So AC and DF. So AC and DF, let's choose these two. So let's choose AC and DF. And now let's choose CB and FE. So CB and FE. But the letters might complicate this, so let's just use the real names instead. Now, by the way, I want to clarify one thing. I hope all of you know that in this scenario, only the direction of these velocities is different. So all of them are equal. So the magnitude of VB is equal to the magnitude of VA, right? So I hope you guys know this because the magnitude is equal, only the direction is different. So AC is going to be change in V, DF is going to be change in S. This is change in arc length. And CB is going to be VB. But I just literally said that it doesn't matter what if you write VB or VA because the magnitude is the same. So we are going to write it as V. Do you guys understand why I wrote V? Does anyone have a confusion about this? Please tell me. Does anyone have a confusion why I did not write VB and I wrote V? Great. What about the rest? There's only one answer. Come on, guys. Okay, that's amazing. Now, velocity is going to be divided with the radius. Now, let's move the sides. Let's actually make change in V common. So if I move change in V to one side and the others to the other side, we are going to observe this situation. Now, in circular motion, we just have this obsession of dividing everything with time. So just like we divided before, now, this time we're not going to divide it with time. We're going to divide it with change in time because this is change in velocity. This is change in arc length. Now, what is change in velocity divided by change in time? This should be a deja vu. This should be like something that clicks. So what is change in velocity divided by change in time? Does anyone know? Okay. Exactly, Aima. This is going to be the acceleration. So this acceleration is our centripetal acceleration. Now, what is change in arc length divided by change in time? This is change in, this is displacement and this is time. So what is this going to be? Can anyone tell me? What is change in displacement divided by change in time? Exactly. It's going to be it's going to be velocity. It's going to be velocity. Now, we have velocity here as well. So what we're going to do is we're going to multiply these two, and we are going to get V squared divided by R. And that is, my dear friends, I guess, because I'm not really a teacher. So this is how we derive the centripetal acceleration. Where does R come from? So Rayan, do you see this FE? Do you see this FE? Can you please answer? Do you see this FE? Now, this FE is my R. Do you understand this? So we had these two triangles. You can see these two triangles. So this is the triangle with the velocities. And this is the triangle with the radii. So these are the radiuses. Now, what I said before is I am using the concept of similar triangles. So AC is similar to DF. So I divided change in V by change in S. And this side, CB, is similar to FE. So therefore, I divided the velocity by the radius. Do you understand this, Rayan? Rayan, do you understand now? Please answer. That's amazing. Okay, so does anyone have a confusion so far? Because we have literally done one of the trickiest parts of, theta is to be small. Only when theta is small. This is very crucial. Okay, so does anyone have any kind of confusion at all? Because this is literally one of the most confusing topics of circular motion. Okay, I need a reply from everyone. If you don't have a confusion, just answer with a no, so I can know that you don't have a confusion. Okay, so Sabina, I'm going to answer your question. Okay, so Aima, the thing is that I have done the past papers of circular motion. I'm going to answer to you, Sabina. Just give me a second. So there's not a single question so far that asks you to derive this, but they can ask you to derive this. But the most important part is that you have this concept. The concept is the main thing. Derivation, if it comes, I'm going to tell you. Okay, so answering Sabina. Now, Sabina, do you remember last time I said that our car was moving in a roundabout, right? So our car was moving in a circular motion and both of the speeds were equal. So the speed is constant, but we know, let me enlarge it for a second. So let's grab it all and let's make it smaller. Just a second, LOL. Okay, so I'm gonna make it all smaller. Hey, why isn't it doing, okay. I'm just gonna erase this. Okay, so Sabina, just for Sabina. Okay, so look, this was our car and this was our, let's say these are two velocities. This is VA and this is VB, right? Now, before I said, let's imagine that this is a yo-yo and we're spinning the yo-yo and it's moving from point A to point B. Now, the speed is constant, right? So the speed is constant, but the directions of velocities are different. So these two lines, this means the magnitude. So what I'm actually saying is that the magnitude of the velocities are the same. So both of them are V in terms of magnitude, just the magnitude. But VA, vector VA, is not equal to vector VB. This arrow represents the vector and these lines represent the magnitude. So only the speeds are equal, the rest is different. Do you understand now, Sabina? Just the magnitudes are equal. So V is not actually equal to VA, it's equal to the magnitude of VA. So Sabina, do you understand? Please answer so we can move ahead. Oh, Sabina, are you there? Okay, sure. So she's not connected with the audio. So anyway, I'm gonna get back to you after the class. So I guess that's pretty much it, everyone. It was a great class. If you have any confusions after the class, you can just send in the group. We're gonna be making, in fact, we have individual A2 and A1 groups on Discord. So have a nice day and bye-bye. Allah Hafiz. Allah Hafiz. I hope you enjoyed the class. See you all tomorrow. Come revised, by the way. All right, I'm ending the meeting. See you all tomorrow.